Earth's crust is a source for a wide variety of useful and essential minerals. Most people know that copper is used for electrical wiring, and gold is used for jewelry. But most people are not aware that the main ingredient in cosmetics is a powdered form of the mineral talc, or that the mineral quartz is the main ingredient in glass. In addition to the economic importance of rocks and minerals, events such as volcanic eruptions, mountain building, and earthquakes all involve these earth materials. A rock can be defined simply as an aggregate of one or more minerals. The term aggregate implies that the minerals are found together as a mixture in which the properties of the individual minerals are retained. Although most rocks are composed of more than one mineral, certain minerals are found by themselves in large impure quantities. In these instances, they are considered to be a rock. By contrast, minerals are defined as naturally occurring inorganic solids which possess an orderly internal structure and a definite chemical composition. Based on our definition of a mineral, evaluate the above statement. Nearly 4,000 different minerals have been identified. Fortunately, for students who are beginning to study minerals, no more than a few dozen are abundant. Collectively, these few make up most of the rocks of Earth's crust, and as such are classified as rock-forming minerals. The most common group of rock-forming minerals are the silicates. All silicates have the same fundamental building block, the silicon-oxygen tetrahedron. The silicon-oxygen tetrahedron is not a compound, rather it is an ion with a charge of -4. In nature, tetrahedra form neutral chemical compounds, minerals, through the addition of positively charged ions. In this way, chemically stable structures are produced, consisting of individual tetrahedra linked together by positively charged ions. In addition, the tetrahedra may form a variety of structures by sharing the oxygen atoms between silicon atoms in adjacent tetrahedra. Notice that in this chain structure, each silicon atom is completely surrounded by 4 larger oxygen atoms. Also notice that 2 of the 4 oxygen atoms are joined to other silicon atoms, whereas the other 2 are not shared in this manner. It is the linkage across shared oxygen atoms that joins the tetrahedra into a chain structure. Other silicate structures exist. These include double chains, sheet structures, and complex three-dimensional frameworks. By now you may have noticed that the ratio of silicon atoms to oxygen atoms differs in each silicate structure. Minerals composed of isolated tetrahedra have one silicon atom for every 4 oxygen atoms, whereas in the single chain, the silicon to oxygen ratio is 1 to 3. And in the three-dimensional framework, the silicon to oxygen ratio is 1 to 2. As more oxygen atoms are shared, the percentage of silicon in the mineral increases. Silicate minerals are described as having a high or low silicon content based on the ratio of silicon to oxygen. This difference in silicon content is important, as we will see when we consider igneous rocks. Like the silicon-oxygen tetrahedron, most other silicate structures are not neutral chemical compounds. They are all neutralized by the inclusion of positively charged metallic ions that bind them together into a variety of crystalline configurations. The major groups of silicate minerals and common examples are shown above. Notice that each mineral group has a particular silicate structure which determines the cleavage it exhibits. Because the silicon-oxygen bonds are strong, silicate minerals tend to cleave between the silicon-oxygen structures rather than across them. For example, the micas have a sheet structure and thus tend to cleave into flat plates. Quartz, which has equally strong silicon-oxygen bonds in all directions, has no cleavage, but fractures instead. The silicates are generally divided into 2 major groups on the basis of their chemical makeup. The ferromagnesian, or dark silicates, are minerals in which ions of iron and/or magnesium join their silicate structures. Because of their iron content, ferromagnesian silicates are darker in color and have a higher specific gravity than the non-ferromagnesian or light silicates. Other important rock-forming mineral groups include the carbonates. Calcite and dolomite are commonly found in the sedimentary rocks limestone and dolostone. 2 other non-silicate minerals frequently found in sedimentary rocks are halite and gypsum. Both minerals are found in thick layers, which are the last vestiges of ancient seas that have long since evaporated. Although scarce when compared to the silicates, other mineral groups are important economically. These include the oxides, sulfides, halides, and the native elements.